Okay. Um, Hello, my friends. We continue chapter one and the lesson, the data science life cycle. So here we want to learn about reframing a business problem as a data science problem, and how to prepare and model the data. Um, for this, we're going to follow a step-by-step scenario today, and also we talk about how you could communicate the results and visualize your data. So the first question that you have to ask yourself is that what is your approach towards data science and data analytics problems? Um, if you have an analytical problem, if you have a problem to be solved, um, is there a model that you're going to follow? Is there someone you're going to ask for? Do you know if there are any steps, 1, 2, 3, 4, 5, that you're going to follow? Do you have any idea about that? Share your thoughts and let me know if, for example, someone asks you to try to use machine learning to predict the weather for Regina, then how would you do that? And what is your approach? What is the first step, the second step, and so on? Have you done something like that before? So think about it and share your ideas. So before we ask that question, we're going to talk about some um, different roles that are important for a data science project. So it's not just the fact that we need a data scientist to be able to complete the project. The first step is to make sure we have enough resources and the people that are going to be involved in the project so that we could complete the data science project. Um, if being a data scientist is your goal, then you need to make sure that you think about other users in a company that are going to help you as well. So usually we start with someone who is a project sponsor. So the project sponsor is the person who is trying to solve that problem and who pushes other people to solve that problem. So probably that project sponsor is going to solve a problem for a business user, and that business user is someone who is currently using kind of a scenario or using I don't know, manual tools, Excel spreadsheets, or maybe they don't even are they're not even able to predict the future. So the project sponsor basically tries to solve a problem and approaches the whole team and gives the problem to a project manager to be able to manage the whole project. So the project management manager tries to talk with everyone in the team to make sure that the project is going as planned. So there are some other people that are going to be involved in a data science project. When you go in a company, or if you have experience being in a company, you will see that a business intelligence analyst who is a person who knows a lot about data, how to analyze them, is going to be there. And also, if you want to start solving a problem, not only you need to work with all these people, but your two best friends and the two type of two roles that are you're going to work with a lot are the DBA, a database administrator, and a data engineer. So a DBA basically gives the access to the data. So if you need to know what's happening with data, if you need a new table, all that, the DBA could help you with that. And the data engineer is going to enable your project to be working flawlessly from the input to the output. So a data engineer nowadays involves with different ETL kind of processes, so extract, transform, load, and also if there are any real-time data analysis, then data engineer is going to help you. So if you want to store that huge amount of information, the one that we're talking about using the Walmart's data, the data engineer is the person who is going to enable the data to be stored and should be able to take care of that. So this is the whole ecosystem of different people that are going to work on a project and make sure it is successful. So data scientist is just one part of it. There are some models now that helps this interdisciplinary team to be able to solve a data science problem. One of these approaches is Microsoft Team Data Science Process, which Microsoft's published. As you know, this is, I don't know if you've heard of it or not. So nowadays, most of the companies use an agile process. So in agile methodology, compared to a waterfall approach, so waterfall approach is that you kind of have these different steps, and you follow those steps one by one, and then you reach the end of the project and your goal. But that approach is not successful if some part of that process needs to be repeated. Because of that, instead of designing the approach as a waterfall process, a step-by-step process, we kind of designed it as an agile process. Like there's a kind of a circle here. Sometimes we need to move from one step to another step, come back, repeat an experiment. So that is quite common. So the first step in the data science process is using this method is business understanding. So you need to understand what's happening in the business. So your friends are the business user, the project sponsor, a business analyst, not necessarily business intelligence analyst. You need a business analyst. And also the project manager could help you to find those people. You need to understand what's happening in the business and what is actually the need of the business. If you think a specific project is so cool, everyone is talking about, I don't know, face recognition, everyone is talking about, I don't know, deep fake or robots or bots or like all these things, and you want to provide that, I don't know, deep fake solution to a bank whose most concern is mortgage applications, then those things may not work together very well. And at the end, no matter how cool and how sophisticated and how complete your solution is, because you didn't understand the business properly, then your solution is not going to be helpful. So after you understand what the business needs are, then you could start getting access to the data, start accessing data and try to understand it. So you may want to start accessing to on-premise and cloud database and files. You need to make sure that you have access to what you need. If there are some real-time data, you need to make sure that you have the required pipeline. If you have streaming data or batch data, these are the different options that you have here. So on-premises means the data is in the company itself. Cloud means that the data is actually in a cloud environment, which is a data center. A cloud is basically a data center. So a data center that is physically secure. So if you have a data center that is secure in different terms, then and it has access to a big network, then a computer that is sitting in that data center, so this is a data center, then you may want to get access to some of the resources in that data center. For example, there might be storage or computing power there, and you may want access to that remotely. So you're sitting at your desk, and you just go and try to browse the internet, and you're thinking that, well, you need some additional resources, a computer. So you go to a cloud, for example, there are many of them. There's AWS, there's Google Cloud, there's Microsoft Azure, and so on. And you ask them to give you basically some resources to do your computing or to store your data. So those resources will be provided from the several data centers that they have across the world, and they're physically secure, they're enough redundancy, and that is going to basically be the concept of cloud computing and how you could access some storage, some services from different cloud providers, data centers, via a centralized location. If the data is actually stored on the company itself, then that is called on-premises or on-site data. So you need to make sure that you know the location of the data sources that you want to get access to. So in data science, the most important thing is data, like, getting access to the data. So this is a very important part of your problem. So again, there are different environments that you may want to work on. Depends again the type of the cloud. You have to make sure that the environment is right. Then you may want to explore the data and try to clean some of the data sets because they may not be in the format that you require them. The other step is that when you are getting access to the data, at the same time, you may want to get access to some data and start building your model. So what is a model? A model in data science, a model is a mathematical or machine learning code or model solution that enables you to learn from data and predict new and unseen instances. So what that means is that, for example, in terms of predicting the weather for the next day or the next week, you have access to the weather data from the past few years. So you know about the weather data in 2019, 2020, and maybe 2021. If you have that data, then you want to predict what is going to be the weather data for 2022. So this is your data that you have access to, and then you want to create a model that learns from that and then can provide you the same data, similar information for another year. So this is a machine learning model. That model is basically a function that could provide you that information. And in order to do that, the first step is to do some feature engineering. So where in that data am I going to look for the important features that is needed for me to predict the new instances better? So that is one important aspect of it. The other part of that, of modeling phase, is training your model. So after you found what you need from each of those data. For example, for weather data, if you want to predict, then your features would be maybe wind, temperature, day, month, location, and then your model is going to learn from that. Like usually a time series model is going to be a good model for you, or LSTM if you're going to use deep learning. And then once you do that, you could predict the data in the future. But an important question arises, and that question is that, how do I know if my model is good or bad? So is it a good model? Is it a bad model? So how are you going to understand that? So that is an interesting process, and we call that the model evaluation. So in the evaluation phase, we basically try to cross-validate and try to run different experiments. Sometimes we do A/B testing, test new techniques, and we try to use different metrics such as true positive, accuracy, true negative, or precision, specificity, and also like there are some scores like F1 score, there's the G score. So there are many different kind of scenarios for model evaluation. And basically, when we go there, the goal is to make sure that your model is as accurate and precise as possible. So these are technical terms that are defined, but in general, we just want our model to be accurate or precise. The issue here is that because we're not in the future yet, it's hard to tell how our model is going to perform on real world on-scene data. So the way that we evaluate our machines and models are that we go ahead and take a look at our training data. So this is all the data that we have, right? So we've got 2019, 2020 data, and then we're going to see if our models could predict future. So we take the whole data that we have. In this case, for example, I take the 2019 data and use that data to train my model. And then I use the data that I already have, and I know that data, I know the correct version of that data, and I try to use my model to actually predict an estimate of the data for that year or for future. So when I create that estimate is actually going to be either close to the actual data that I already know about, or could be far off. So if my model is predicting the future quite like accurately, then I can say that my model probably going to predict the future on-scene data good, like reasonably well. If it's not good enough, then I have to change my approach, change my model, train it better, and so on. There is always some error. So this there is a difference between the kind of the output that the estimate that my model generates and the actual data. And the difference between them is actually the error rate, or the residual and the error that we get from our model. So there's always a difference. There's always something off, something not working properly. And that's why this whole model building, everything is an iterative process. So we want to, the goal here of why the reason that we go to data acquisition again, try to build a model, try to understand the business, is to minimize that error. So the difference between the actual data and the predicted data using our model should be minimized. And that's the goal of everything that people do in machine learning in general. So once you create a model that is accurate enough, then you need to show it to business. You need to make sure that it satisfies the customer. And so if the customer is satisfied with that, you could deploy your model in a cloud environment in somewhere that is accessible, like you could use web services or a place to store the model. And there are some intelligent applications that you could also use. And then you could deploy it. And if the customer said that, well, this is what I want, then that's the end of your process for that specific iteration of improvement. This process could end, but you need to continue scoring and monitoring the performance of your deployment, because as new data comes in, everything changes. So imagine, for example, you know about the pandemic, right? Imagine I have the average number of visitors to Canada. So there are, for example, in 2015, 2016, 2017, 2019, the average visitors per year are 1 million, like 1.2 million, 1.3 million, 1.4 million. And then I build a proper model last year that when I give my model this data, it can accurately predict 1.4 million, right? Now I say, okay, I'm going to use the same model, and this time I'm going to see if I could get the past 3 years, like these 3 years, and trying to predict the number of visitors in 2020, right? So if I build that model like 2 years ago, oh, sorry, I missed 18 here. Sorry. So, so if you are going to use this data and then you're going to predict the like the 2020, then something that is very important is that you did not know about the pandemic, right? So a pandemic, which is a new thing, like your model is deployed, everything is working properly, but then suddenly a pandemic comes and this virus actually tries to change all the equations. So because of that, you have to continue updating your model. Even though if you have deployed it already, you need to make sure that using new data and using new information, like the whole border is closed, like all the airlines are not working properly, things are not like it's a pandemic, right? So you need to create a new model. That's why everyone is concerned about the new models, because all of the old models are not working anymore, and the equations are all changed. So that that follow-up after the deployment is also quite important. So make sure you, even after your customer accepted your solution, you continue to monitor your model. So the other way that we could talk about this cycle and this process is a data analytical life cycle. So that was a model that we had there. Another model, there are many models that are being used for data science. So this is kind of another model that we could use, and we're following to make sure that you understand each step that you need to follow. So the model that we're kind of using is a 6-step model in a circle, and the same way as before, it starts with the discovery, data preparation, and data modeling, model building. And there are two important factors here as well, which is communicating the results and operationalizing. So we go through each of these steps quickly. In your projects, you need to follow each step. And now, while you're hearing this, think about your proposals and your projects, because this is very important, and this is how you're going to present, how you're going to write your proposal. So you need to think about the discovery, what is your problem, what are the different data preparation, data model building steps, and so on, until you could communicate your results. So the first important problem that you have is to discover the actual business problem and try to draft a business problem statement. So to understand this problem, to really write that statement, what you need to do is to conduct stakeholder interviews. So stakeholders are people who care about the solution, who have something in their mind, who want something to be developed. So make sure you ask them questions and listen carefully. It's very important to listen more than you talk. I mentioned that again, that listening is a very important skill for you to have, especially in the discovery phase. You may want to think about solutions at this stage, but you want to hear what their problems are and to see what they have tried before, what worked and what didn't work. Then you need to reframe that problem as an analytical challenge. So what is the problem, and then how we could solve that problem. That is also an important phase. The other thing you need to make sure is that you want to know what resources you need and what are their availabilities. So in terms of data, people, and you need to create a plan. So your plan should involve different steps, step 1, 2, 3, what are you going to do in each step? Okay, I need to talk with this person, I need to talk with that, I need to add access to that data, blah, blah, blah. Then I'm going to create a, get access to the data, create a sandbox, create my model, evaluate my model, then report everything. So basically, the big steps, the 6 big steps that you have are the steps that you have here. So from discovery, data preparation, model planning, model building, communicating the results, and operationalizing. So these are the key activities that you do in discovery phase. So let me give you an example. Imagine that you're hired by a bank, and they are going to provide you a scenario, and they want you to try to solve a problem. So the scenario that they give you is an online mortgage approval scenario. So when you listen carefully after like a long period of time that you successfully listen to like what different stakeholders were offering, you will realize that the problem is that they want an automated mortgage application pre-screening service. So what they need is that they want online mortgage applications to be flagged. So mortgage is a so you all know that, but a mortgage is a kind of a loan that you get for to get a home, your home, and they're usually quite large. I guess usually around $400,000 to, I don't know, $2-3 million. So when you want to buy your home, a lot of people want to qualify for that, and they have to make sure the bank needs to make sure that they all have access to the they all have access to the they all have access to enough resources in terms of down payment, and the clients can actually pay back the bank. So for a mortgage that is around kind of, let's start with a small mortgage, which is around, I don't know, $250,000, which is not which is a really small mortgage. If you want to pay this back over 25 years, okay, usually there's interest involved, which is right now, or maybe like it's between 3 to, I don't know, 5, 6, and it could be over or less than that. So there's an amortization process, and when the interest is added up to this amount, even at 3 or 5% over 25 years, usually an amount like that ends up being something like $400,000 or more over kind of 25 years. So that is more than, I guess, I don't know, that's around, so each year there is around $20,000 that needs to be paid. A little less than that, like, I don't know, 18 or so. I would say it's 17, okay? So each year, this amount needs to be paid for that small mortgage. So for a person to be able to pay that, they need to be able to pay, I don't know, at least $1,500 a month. So that this is going to be uh, something that not everyone could afford, because they may have other loans, they may have a car loan and things like that. So sometimes people think that they can buy a home, and just imagine that that amount is doubled for the average home price, for example, in British Columbia is over $1 million. And when you kind of consider the fact that, well, to buy an average home in British Columbia, Vancouver area, you need around maybe $1 million mortgage or so, then that is more than 4 times that amount. So you need to pay $6,000 per month to be able to afford a home that is that has that a $1 million mortgage on it. So not everyone could afford that, because for something like this, you need to have imagine that there is tax involved as well. So to be able to pay that, someone needs to have pay $72,000 a year, which that is after tax. So a person should at least have, I don't know, like around $100,000 per year salary, spend nothing out of it to be able to buy an average home in British Columbia, like in Vancouver area. So a lot of people try to apply, and well, the reality is that, well, you can't just, even if you have a very good job, then you can't, all your money goes for that mortgage, right? So so they deduct everything, and then when they actually go to try to go to the bank and try to get the mortgage, most of them will fail anyways. So the problem that you have kind of addressed is that the bank has so many different applications, and those applications are more than the amount that an underwriter could potentially screen in real time. So when people send online applications, one underwriters try to process them, but the problem is there are 5 times more online applicants than we have underwriters. So when the underwriter is trying to process all these 4 rejected customers, the one customer that was actually eligible could churn and go to another bank. So that's a bad thing, because what the bank wants is to, because they get interest as well, they want to get access to that specific customer, which is the top 20% customers that they have. And they want to find that customer and redirect them directly to the underwriter instead of trying to monitor everyone. So that's the data science model that they're looking for, and you need to provide that to them. So this is kind of a business understanding and how you could model the question and reframe that as a data science model. So after you've done the discovery phase, there is the data preparation phase. So in this phase, you try to establish, the first thing you want to do is you want to get access to the data and also establish the analytical sandbox. So what is a sandbox? You cannot work on the data that is directly being used by the company, and also you need to have a place to play around with data. So imagine that the company or the place that is storing the data, they have like this big database, and this database has all real-time data being processed in there. So there are customers connected to it, like it's real-time data, is very critical data that goes in and out of it. And then you want to get access to like a big chunk of it, and you want to work on it, and then you need a place to actually put that copy. And not only one copy, because you're going to transform it in different ways. And there are multiple copies of that, which eventually become quite big. And because of that, you need to establish a sandbox. A sandbox is a place that you could access the data, get copies, transform it freely, and that has like maybe 2, 3, up to 10 times larger space than the data that you're going to work on. So that's the first step that you want to do. You want to establish that analytics sandbox. And after you establish that, then you need to extract the data from the database, transform it to the way that you like, and load it to your sandbox. So then when you're in your sandbox, then you want to transform the data again. So the regular methods in business intelligence, you have ETL, or extract, transform, load, but in data science, you also have another transform at the end, because that's the main part that you're going to do. Then you can start exploring the data, try to do some data conditioning, merging, and removing some outliers, missing data. There's always some missing data and outliers in any database, so you want to get rid of them or handle them in some way. And also, in this phase, like in data preparation phase, you want to try to summarize and visualize the data, which is also very important. We'll see how. So in order to do that, explore the data, there are different tools that you could use. There are online tools, there are offline tools. Now that you all know how to, Python a little bit, this is very important that you try to start using it. Some of the good program languages that are suitable for data science are Python and R. There's also like Julia that is becoming popular as well. And there are some tools that you could use. It is very important to mention the fact that data science is sometimes an art as well. So communication is important, and you're communicating technical data. If you want to communicate technical data, if you just have some code, that's not enough. And if you have just an interface, that's not going to be enough as well. You want a combination of both data, like details, and also visualizations to tell a story. And that story is how you found a problem, business problem, how you try to solve it, and what are the results. The best way to, so far, one of the best ways that data scientists have found and they're using to tell that story is using something called a notebook. So a notebook is a combination of code that you could write and plus the visualizations. So these two combinations are basically going to give you enable you to tell a story. So from the top to bottom, you can tell a story one by one, and you could and anyone, if they have some technical knowledge or if they don't, they could go ahead and take a look at what you've done. And you can see that it's not hard to find out what's happening here. So this is a plot here, and that plot is, if you look at here, it says that, okay, I want to have a count plot on the funded variable and the count variable. So it's not hard to read this data, even though if you do not know what Seaborn library is or how to use this. So one great way to for you to install a place to work with notebooks is to on your machine is to use Anaconda, install that. That's a library that has the latest version of Python and the latest version of Jupyter Lab, and there are some other IDEs as well. There's also Google Colab that you could use, and they're all going to help you with that. This is the This is the Anaconda Navigator. After you install it, you can just run Anaconda Navigator, and it will bring you a Jupyter Lab, Jupyter Notebook, and like RStudio even. You need to install R for that. So these are all some of the tools that are available to you. So when you click on the Jupyter Lab, what you get is that if I bring that here, yeah. So this is the Jupyter Lab that is actually started. So you have this example on UR courses. Go ahead and download it. And there is a file, and also there is this IPython notebook. So you can come here and you can run all the lines. You could just press Control Enter on each line, and the results will be provided to you. So each of the steps, so I put some of these steps in the PowerPoint, but you need to go ahead and try to run the rest of the steps to make sure that you understand what's happening here. I think here we've tried some different classifiers from like decision trees, logistic regression, K-NN classifiers, and here we're going to visualize some results. So these are all different things, and I've got the code of this one to make sure that we found the best K for K-NN. So make sure that you go ahead and try to run these to become familiar with the process. So the first step is for you to try to load the data. The way that you load the data is that you could use a library called Pandas. So Pandas is a library that allows you to work with spreadsheets or data frame. So what they usually call them data frames. The data frame is something similar to what you have seen in Excel. It's just like a table with different columns as variables, and also the rows are going to be the data that you have. So this is the mortgage fund.csv file that you could quickly use one command, pandas.readcsv. You should all know that when we say we import pandas, this is importing a library as PD. That's a short version or alias of pandas that everyone are using, and also for matplotlib we're using PLT. So pandas read CSV, we read that CSV file, and we just use display and mortgage head. Head will print the first 5 like rows of your data set. You see from 0 to 4. So that's display mortgage.head. And mortgage.describe will give you some statistical analysis on each of these columns or variables that you have. You may ask, okay, what do these mean? Like, what is funded? What is rate? What is different things? So you need to make sure that you go and try to get access to the background of the data and the details of what are the different variables. What do they mean? So usually you get access to this data by talking to the business and the data owner. That, okay, what does flag mean? What is this? Sorry, what is funded mean? What does the rate mean? So in this example, funded, this is the example data that for example, bank provided to us. So this is about the previous applications and whether those applications were funded by the bank or not for different reasons. Whether the customer ended up taking that loan or mortgage, or the bank was ready to do that, or similar things. So this is funded means that application is funded or not. Rate is the rate that is provided by the bank, and competitor rate is the least rate offered by the competitor bank to the customer. So if another bank offered your customer a 2% loan, then if you offer them 5.61, that will it's obvious that the customer will not take that. So that's the reason that it has not been funded, or maybe some other reasons. The amount is like the amount of the mortgage, like that is around $636,000. This is $100,000. This is $844,000. The location is the location of the mortgage, which we do not know what that means. Risk score is the risk score of the clients. So that could be, we don't have any information whether higher is better or lower is better. And the you could look that up. And number of products is if the customer had any products with the bank. Usually if a customer has more products with the bank, it's probably that they choose that bank for more products. It's easier to work with them. And some segmentations of customer by the bank, which is provided here, that could also be a factor whether that mortgage is funded or not. So this information is from the previous years. So what we want to do is we want to use this data, like some of this data that is provided to us, like this information, other than the funded. Okay, so I guess this information will be the input to your kind of program and your model, and this is the output that we want to basically predict. So this output that we want to predict is we already have that for the previous years, but if we get this input for new data, then we do not have this information, because this is the part that our model for any new data should get all this input and try to kind of predict that output. So that's why we want to be able to do that using by creating a model. So the first step was to access the model, and we got access to some statistical properties. But there's something very important that you should consider. Sometimes statistics may not be enough, and you should not just rely on them. Look at these 4 data sets. So when you look at the data set here, this is a very important, like a famous case. It's called Anscombe's quartet. And these 4 data series, like you see X and Y's, these are 4 different data sets that are provided. You can see that the X is different here and Y is different, and they're all different data sets, 1, 2, 3, and 4. The important factor here is that most of the statistical properties of these data sets are equal. So the mean of X in each of those data series are equals to 9. The exact variance of X in each case is 11. The exact mean of Y in each case is 2.5. The variance of Y in each case is 4.13. And the correlation between X and Y, like how they, like if you want to get from X to Y, is again in each case the same. So it's very important that when you want to predict data, like if you want to plot this and you create a linear regression line in each case, the line is exactly like the usually the line is the same line. So when you try to plot them, and this is X and Y, and there are different kind of points here. The line that kind of predicts them all using linear regression is the same line. So it seems like that these four data sets are statistically quite similar. So if we end our investigation here, we may come to the conclusion that, well, they're indeed similar. But if we come here and try to plot these data sets and try to visualize them, we'll see that these data sets are quite different from each other. And they have different shapes with different meanings. So this is the first one, this is the second one, the third one, the fourth one. So this looked like to be some kind of a regular data set with data around that line. And look at this one. This is not linear at all. This is a non-linear data that definitely shows a curve. This one is quite, you see that this data seems like to be in another line, totally in another line. And there is one outlier here. And this is exactly the same case here. There is an outlier here. And look at this. All the data, most of the X, look at here. Most of the X here is just 8 with different Y's. So, and that is an outlier. This is an outlier. This is another shape. So these are all different data. And you may want to, when you look at these, you may want to consider the fact that, oh, maybe that is a typo. You know, or that is another, like that is something else. That is the data that is we want to consider, we want to take a look at. Here it's more kind of a regular kind of a data set with some noise, but these shapes are different. So the point here is that you want to visualize your data before analyzing it. It's very important because that is going to provide you with a lot of information. So another reason that visualization is important for us is that basically human beings, we are visual beings. So we understand visual concepts sometimes better, most of the times actually better if the visualization is good. If the visualization is bad, then we may want to just stick to numbers. That is easier to read in visual form, and sometimes it helps discover new knowledge. So you just saw that how visualization helps us discover new knowledge that was not available if we were just looking at the data. Applies to any domain, so whatever you do, visualization is helpful for you, and it also helps in analysis and communication. So you could usually do that to communicate data. Sometimes, like most of the times, when you want to visualize a very big variable, a variable with a lot of different values, maybe 100,000 values, then visualization is your only way to try to see what's happening. So if you have a single variable that you want to visualize, you could use a plot, or you could use a histogram. What we have here is a histogram. A histogram actually tries to create some buckets, so some buckets of different values, and then tries to count the number of times a value of a variable falls into that bucket. And for example, this is the histogram for competitor rate. So this is the rate that is offered by different competitors. And when you visualize this, you will see that there is something off here. So most of the, if you try to look at the data, it should kind of show you kind of a normal distribution. But if it doesn't, it's not the case, then you may want to investigate why. For example, here, you will see that we've got a lot of rates. We've got quite like around more than 15,000, like 16,000 values that are negative. So that's a negative rate. And what does that mean? What does it mean by negative rate? Like you borrow money from the bank and bank pays you something back because you borrowed some money. So you want to investigate what's happening. Is that misinterpreted data? Is that data that people did not know? Is that just -1? Just if they didn't have any competitor rate, did they just put -1? Or is it negative amortization? Is it missing value? What's happening there? So you need to make sure that during your discovery phase, you visualize the data and make sure that you have answers to most of your questions. Then you want to there is the negative rate, like that is not a myth, but we just want to make sure that this is the case or not. The way you can do that is that you could go ahead and this is the data frame that you created by loading that, and you could say that you want to create a histogram on a specific column and variable, and you could just set the title and then show that. So another way to visualize the data, if your data is like not necessarily kind of a rate that you could count, and your data is continuous, you could use density plots. So density plots are similar to histograms, but it just tries to estimate the distribution. So KDE is kernel density estimation of a specific variable. You can see that how you're creating these. So again, it's the same thing. You can take a look at the shape of this distribution. Just make sure that things look normal. If you have any outliers or anomalies or anything like that. So if you take the density of a mortgage, like what you see here, you can see that this looks to be skewed. So this is skewed to the right. So you could see that here you have a very long tail on the right. So it's skewed to the right. And like you have a kind of a sharp edge here. So this usually happens if you have very large values. So you see that for some big homes, people got like 3 million mortgages, 2 million mortgages, 1 million mortgages. But most of the mortgages were around, I don't know, like maybe 500,000. So if you want to work with data, well, that distribution is not ideal. So it's better to try to kind of condition this data. What you can do is you could try different things. Like this was the a question for the final exam that I had in the previous years. So if you want to get a better distribution and your data has very large values and your data is skewed, you can try getting the log or a square root of the data. And then when you get that data, it's the same kind of a sense of data, but you can see that you have you have kind of a better distribution here. So the log here does not work that great, but SQRT, square root works better. So you can see that this is kind of a way that you could start pre-processing your data and make more sense of your model. So that was for one variable. If you want to visualize the relationship between two variables, you could use a scatter plot or a Higgsbean plot. So a scatter plot, this was again a question for the final exam. So scatter plot and the Higgsbean plot, they help you analyze two different variables. And these two different variables, you could just put them here. Sometimes the scatter plots become quite a little hard to analyze, and then if you have high volume data, then you'd better use a Higgsbean plot. The scatter plot looks something like this, you know. And then if you have a lot of them, then like something like that happens. But then a Higgsbean plot tries to group some values together. It's like a histogram, and it's going to give you a better shape. And it's easy to, again, plot. You say mortgage.plot, hex bin, and X is rate and Y is competitor rate. You give a grid size, and then you give it an access. So the code is in the notebook that I provided to you. And you can see here that the rates, like most of the competitor rate and rate, like they've been around this area. There was a high count that our rate was around maybe less than 2, and the rates were around a little bit over 0, which means that a lot of mortgage applications probably were not funded, because it seems like just visually, it seems like if customers have a better rate, they go with a better rate. So the next part of the data science lifecycle, the 2, 3, 4 ones, are model planning and model building. So these two parts are very close, and then you've got these two are close as well. So in model planning, what you need to do, you need to take a look at your data and decide what are the variables, what are the attributes that you want to use in order to build your model. So we could call that feature engineering. Some people call that, or variable selection. So one important part of model planning is to try to see what are the important factors, features that you want to use to predict your output. So here is where we decide what is our the variable that we're going to predict, which we call it Y, and what is the input, which we call it X. Why do we do that? Because we're trying to create a function of X, and that gives us a Y as the output. Again, if I want to write it and show you in another way, your model, this is your model, is a function of your input. So you provide it with your input, and it gives you the output, right? So this is kind of a model that you want to create. So in a machine learning, we don't know what that model. This is the problem that we have. For a start, we know this. For historical data, we know what is our X and what is our Y, and we try to find that model. What we can do, like what we usually do, is that we take a look at these two variables, and using machine learning, we try to get an estimate of that function. That if we provide it with X, it could give us an estimate of the true Y's. So this function is created using machine learning. And once we create that function, this is the way that we try to find or estimate that true function that we have there. Then once we create this estimate, we want to make sure that this estimate is quite close to the other one. If they're kind of rather close, then we could say that, well, our estimate is good enough. Sometimes, like it depends upon the application, that the like what a good estimate is. Sometimes the high accuracy is better. Sometimes we want something that has more precision, and etc. We'll talk about that later. But this is the goal of our model. So here you see the reason that we decide that, well, we say that X is those features. The reason we do that is that we want to give the rate, competitor rate, amount, and risk score. This is what we decided, right? We want to provide these to our function, and our function is going to provide us with the answer of whether that mortgage was funded or not. So if we can estimate a function or a model that using the rate, competitor rate, the amount of the mortgage, and the risk score of the applicant can tell us whether that mortgage is funded or not, maybe we could use this model to to pre-screen some of the online applications. So imagine I go online and I put the rates that I got from a competitor, and the rate that we know the rate that the bank is going to offer. And I say, for example, I say that, okay, I'm going to, let me remove some of this stuff here. Imagine that I'm going to try for mortgage for $500,000 and my risk score is 805. And I got a rate from competitor as 2.6%. And from the bank, we know that the bank is offering us 3%. Okay. So of course, there are some other variables that we want to add. One variable, it could be how many number of products, or there were location, etc. We could quickly take a look at the different variables we have here. So these are all the variables that we could use, like the date of the application, the location, risk score, number of products, customer segments. You could choose to include them or not. That's the main activity that you're going to do. If you think they're relevant, you could add them. If not, you may just skip them. The best way is to try different combinations and then to try to see how it works. So this is a new unseen data. So the model, we don't know if something like this is going to be funded or not. So because we don't, the why, whether it was funded or not is a question mark for us, then if we were able to predict this f of the estimate of x, I could just provide this as input to that function, and then it could estimate to a good extent that I'm going to be funded or not. For example, because the competitor rate, I got a better rate, probably the answer is no, I'm not going to be funded because choose not to. Or the bank is not going to offer me kind of a better rate. So once I know that, then that is going to help us to not even send my application to the bank because I'm probably not going to get funded. So if you have any questions regarding this, let me know. Just this is the phase that we're going to talk about this later, and it's also explained in the book as well. So I'm going to focus on that later on to see how we could choose different variables for different scenarios. So as part of the model training, so as you know, one important part was selecting the features, the input variables and attributes that we're going to use. And another important part is the model selection. So, okay, what type of function that f function is? There are different types. There's classification. We're going to talk about them more later, but classification is basically a type of model that allows you to select a specific classes and categories of output like this. For example, in this case, there are two classes, funded and not funded. So these are two classes. They are categorical variables. So if you have categorical variables in the output, then you can use a classification model. Here we use 1 for funded, 0 for not funded. This is actually what you are doing here is a binary classification model that we're trying to build, because binary means there are only two cases. For regression, the way it works is that you have usually you have a continuous variable in the output. There's of course logistic regression that is used for classification as well, but regression in general tries to create an estimate. Remember that linear regression is a good example of it. If we have our x in one axis and y in another axis, and we have just a second. Okay. And we have, yeah, it tries to change the color, not working. And we have we have some inputs, like for a specific x, we have a specific y, and for another x. These are examples. These are the samples that we have. So when we have these samples, we try to create a model. So we try to linear regression. It takes a look at it and creates a model that tries to go through all the lines. So the way it works is that now if I have a new x, so if I've got a new x here, so it's x new, and this is my x, and I want to get the y of it, I could take a look at this line, find out where that line is, and I could get my x of the y of that new, which is going to be a specific number. So it's you see, I could, for each x, I could get exactly a specific number on this line. That's why regression is works best for the continuous data and variables in the output. If you have some data that you want to do some analysis on, you could use association rules and market basket analysis and affinity rules to be able to predict whether some products are going to be bought together or not. We're going to talk about that. And there's also text and image and video analysis that has its own category. There are some deep learning networks that you could use for that. So in general, if you want to know what kind of if you try to understand the problem and the type of the problem that you have, then yeah, I just try to run this again. Yeah, if you know the type of the problem that you have and try to solve, then you can take a look at those problems and see whether you have some items that you want to just group them by similarity, or you want to find some structure or commonality in data. So this is more of a exploratory technique, not a prediction technique. And then you could use some clustering algorithms like k-means. If you want to discover the relationship between some items or actions, you could use association rules. An example of those of that category of techniques is a priority algorithm. Also, we have affinity analysis algorithm. If you want to know the relationship between the outcome and the input variables, which we were just talking about, if the outcome is your y and input is your x, if you want to know what's the difference, what's the relationship between them, there's a line or something like that, you could use regression, different regression algorithms like linear regression, logistic regression. There are more than that. There are lasso or more types of regression. If you have text data and you want to analyze that text data, then you may want to consider the text analysis kind of techniques. There are regular expressions, document representations, such as bag of words, TF-IDF, which is term frequency, inverse document frequency. These are different techniques, and of course we have more complicated deep learning based models, like not necessarily things that are like not necessarily deep learning applications, but more sophisticated ones. For example, we've got word embeddings. Yeah, there are many different techniques for text analysis. If you want to assign noun labels to objects, for example, like if you have categorical labels, the same thing that we had here, we have some labels, whether something is funded or not, and we want to apply that to our features, then you could use a classification algorithm like KNN, k-nearest neighbors, decision trees, neural networks could be used for that. If you have some temporal process, some temporal data, and you want to forecast that temporal data, you could use time series analysis. There are categories of techniques. You could use LSTM, or you could use regular moving average algorithms like ARIMA. Finally, like the newest categories of algorithms are deep learning algorithms that there are other types. Of course, there is reinforcement learning. There are different categories if you want to teach a machine, but literally, if you want to identify face, objects, images in photos and videos, you could use deep learning neural networks. And the major one of them are like regular deep neural networks. There is convolutional neural networks, which are good for images. There's LSTM, which is long short-term memory, which is very good for sequence analysis, data prediction, and there are many different types. So restricted Boltzmann machine, RBM. So there are many different neural network algorithms that you could use for different purposes. So now that you successfully planned your model, then it's time to try to build your model. So what does model building means? So model building is actually trying to train the selected model, trying to train that model using the training data. So training data is actually labeled data. So imagine that your data looks like this. I've got, this is my input and this is my basically output. So for the output, imagine I know if I give x1 to my model, I'm going to get y1. If I give x2, I'm going to get y2. So these are labeled examples. But if I want to basically try to give, if I have like some examples that are unseen, so these are unseen examples, and I don't know what the outputs are, then I could use this label data to train my machine and also test my machine. And that unseen data could be used to basically like test my machine in future, or like just apply my machine to get the output of it. The reason I say that like this label data is good for both training and testing is that I could use some part of this data to train my model, to teach my model how to predict good output and how to create a good estimate. But then I could test my model using another set, And then because I know what the true output is, I can compare that with the predicted output of my model, and then in that way I could realize how my model performed. So when we select a specific model, we need to evaluate the fitted model. Because of that, we usually get our data set, which is like all the label data. So all the label data that we have, we get access to it, and then we try to get around 80% of it for training and 20% for testing. There is another model that's like we could use, I don't know, 70% for training, 10% for validation, and 20% for testing, which I'll talk about later. But for now, it's good for you to know that our label data is going to be separated and split into two sets, usually 80% for training and 20% for testing. So this part is also labeled, but we do not provide the labels to the machine. So we do not provide the labels to the machine, but we wait for the machine to give us the output for those 20%, and then we compare that output with the actual output because we know the labels, and then use that to evaluate how good our model is. So to evaluate the model, we just simply count how many times the model predicted correctly. If the model predicted all the outputs correctly, perfectly, the model accuracy could be 100%. If not, then it's going to be different, and we may need to train it more. So there's a library called scikit-learn that you could actually use, and it has a train test split, and it can give you it can randomly create a test and training and test it for you, which is the xtrain, xtest. These are the inputs for training and testing, and this is the Y for training. So these two, the training will be given to the model for training, and this also will be given to the model for testing, but this will not be given to the model. It is used to compare the output of the model, and we want to know the relationship between kind of these two to see if the model predicted the actual outputs correctly or not. If not, we adjust the model accordingly. In the code that I provided to you, we've used different models such as a decision tree, and also logistic regression and KNN, k-nearest neighbor, to test to see which model works better on our data. So we can see that on the training set itself, like the X of train and Y of train, the model performs very well, like 100%. But when we give it the test set, it does not perform very well because that's unseen data. Like, although we know we have the labels, but the model has not been trained on it. So usually the test accuracy should be lower than the training set. And when you have a training accuracy of 100%, sometimes that means you have an overfitting problem, that your model is actually, sometimes we could call it memorize the data. So there is a concept called bias versus variance, which talks about this fact. You could read it in the book. It's regarding training and how these two different things matter. Usually what it means that to some point, if you train your model more, you will get better results in testing. But if you train it too much, you get a very good score on training, but your actually score on testing is not as great. You could see that here that in logistic regression, because it's just created a linear model, it seems like the training and testing accuracy, both of them are the same. And we also use a k-nearest neighbors classifier, which I'll explain you how it works. And that k-nearest neighbor simply, it doesn't give me 100% accuracy on the training set, similar to that decision tree, but it provides a much higher accuracy among all of the models. So you see that, let's compare these two. So you can see that here on the decision tree classifier, I've got a 100% accuracy on training. On my KNN, I've got a lower accuracy. But when actually I test my model on unseen data, real world data, neural KNN performs better. So this means in general, this could be a better classifier than this one in terms of accuracy. But of course, this is a simple application. There are many other things involved regarding the high memory usage of KNN that we could actually consider. And also make sure that you verify the model assumptions. Some of the times the assumptions of some models are are different than the type of data that we have. For example, in linear regression or naive Bayes, for example, you need to make sure that the data that you have is not correlated, or like in linear regression case, your assumption could be the fact that you think that your data is linear, but if it's not linear, then you may not use linear regression because that may not be your best case. So once we come back here and we try to evaluate our model, then there are many different factors that could be used and could be evaluated. So scikit-learn provides us with different metrics. Again, it's covered in the book. You could go and take a look at it. And there's, if you search for precision recall on even Wikipedia, there's a very good article there that covers different types of it. But there are one of the most interesting, I guess, like scenarios, reports that you could get using scikit-learn is this classification report that if you take a look at here what I've done, then it makes more sense to you. So this part is just I'm importing some libraries, but here after I train my KNN, you see in here, let me show you what's happening here. So I've got a k-nearest neighbor classifier. I just create an instance of it and I call fit. Fit will actually trains your model. So in order to train a model, you provide the X of train and Y of train, because you need to provide the label data so that the model could like train itself. Now, once that training is done, we want to know what is the actual prediction score. So we provide the X of test, which is the input, the test input to the model, but we do not provide the output to it. The model will then try to predict the outcomes, and it puts them in the here, like we put that in the predict library. Now, this classification report, there's also a confusion matrix that you could use, which is quite nice. A classification report will require the Y of test, which is the actual examples, and the prediction, which is the estimate. So the prediction that was given by the KNN and the actuals will be given to the classification report, and the classification report will try to calculate different like metrics here. For example, if the this is the precision recall. Recall is usually how many times, how many of these zero labels were predicted, predicted at all, and how many of these one labels were predicted at all. If a score is a combination of both precision and recall, which gives you a harmonic mean here. So, and in total, these are some of the average ratings that you get. So the average recall is usually called accuracy, and that's why that we kind of have the accuracy of the KNN as 88%. So in this case, everything is 88, but usually that's not the case. And you see it here because it probably we're just lucky that we got 88 for all of them. Usually that is not the case. So we'll cover against these in details later. Just remember the fact that we're going to we need to use different metrics to like provide some report, and we need to evaluate our models. So here I want to talk to you, like try to explain this how one of these models work. So KNN, K nearest neighbor, is a lazy or learner or an eager learner model. So the way it works is that, it's a lazy learner, which is against the eager learners that are other types of classifiers. So a lazy learner means that it does not create a model per se, so it does not create an F and tries to kind of use that function to predict the outcome. It literally stores the data, and when you want to test something, it goes through the whole data set, and tries to find the closest sample that it can find, and trying to find out whether which of those samples are, like, which class that new sample could belong to. So if you look at here, like we've got an unknown sample, and then we've got two samples, which is like a green and red. And it looks at the top K samples. Like if K is 3, it looks at the closest 3 samples. If K is 5, it looks at the closest 5, and tries to realize which one is probably the class, could be the class of that sample. So, and that K could matter because you see if K is 3 here, the class could be red. If K is 5, 3 of those 5 will be green and only 2 will be red. So the class could be different. So the hyperparameter K is an important parameter for this class. So how does it compare? Like, how do I know, how do I get the distance between my new example and the previously available examples? That is what we call a distance, distance metric or distance measure. Usually, like, one default distance is Euclidean distance. So if you have, if you want to get the distance between two variables, 2 points, it doesn't matter, like the distance between P and Q and P is the same, and it is measured using the square roots of the sum of squares of the differences between each of those attributes between those variables. So if in our case we have 4 features, so when we want to use KNN, each of those 4 features, for example, the amount of the mortgage, the risk factor, everything, the difference will be calculated between each of those variables. If you want to compare 2 different samples, the sum of them will be calculated, And then if my new case was, let me see if we have that, or I just remove that. Yeah, I guess I removed that. So if I had a score of, I don't know, 800, and then like my rating is, I don't know, 2 points, the rate that I got was 2.6, and so on. So I have different variables. It goes and compares my case with all the samples that are in the database. In our case, there are around, let's see the count. So the count is 112,612 different cases. So KNN will compare a new sample if this is the whole database and it has access to it per se. At least it compares it with the training data. So it compares with that 80% of that, which is the training data, and finds out the 3 or 5, depending on the K that I provide, finds out the 3 samples that are very close to my case. If there was another person that has the same, like a ratio of 700, I don't know, 79, and the ratio of like the rate of 2.7, so that sample could be a sample that was very close to mine. And if that case was not funded, then probably my case will not be funded as well. So this is just a lazy learner that compares all the different cases, and it basically tries to find 3 similar cases, like if there's any of these in the database, and maybe there's 801, then if 2 of these 3 are not funded, then it's going to choose not funded for me. And usually we choose K as an odd number because it will result in a tiebreaker. Otherwise, like, the algorithm could decide it in another way and just tries to decide based on the closest samples. So you can summarize that with this square root of sum of scores of the differences between each kind of a variable attribute, and I from 1 to n is going to n is the number of variables that we have, and I is the index for each of those variables. So because we have more than, like, we have a lot of different variables, I try to create a case here for you that shows how the rate that is offered by the bank and how the competitor rate could be 2 factors that could affect the closest samples that are chosen for a new sample. So this is the data set, okay? And the in this data set, these are the samples that are already there. So this is the actual data and the actual distribution from the data set. And you could see that for higher rates, if the rate is very high, okay, for most of the rates that we have, if the company the bank offers a very high rate, most of them will not be funded anyways. If they offer a better rate, you see these green areas and this, the applications are usually only funded if the like, you see the competitor rate. This is the competitor rate. So if the competitor rate is low and our rate is low, then it is given to us. But if our rate is higher, the only applications that are given to us is those that the competitor rate was higher. This is the competitor rate was higher than our rate. For example, here I've got a rate of 4 that our bank offers, And if I go here, create a line here, I'll see that if the other banks created, so that is not perfectly visible, but if other competitor banks provided a rate of 4, let me see, maybe yellow. Yeah, yellow is better. So let me give you an example. Imagine that our bank is offering 4 and a score of 4, and then another bank is offering a rate of 2. So if I go and connect these two, that is going to be roughly here. So you can see if the competitor rate is lower, that application is probably not funded. There are some outliers you see here and then that are exceptions, but that's generally the case. So if our rate is lower than 4, but the competitor rate is even lower, then again it's not funded. But if the competitor rate, for example, is 8, then the rate that we offer that is up to around 8 is mostly funded. So I would say that one reason for these high rates could be that the score of those applicants could be low, or any other reason that they were offered a very bad rate and they could not afford it and they were not funded. I don't know, but this is type of these scenarios and examples of how you could use visualization to understand what's going on. So basically, now that we have all that data, imagine we've got a new sample here. And this sample could be, imagine that this sample is around here, somewhere there. And we want to find out what is going to happen and what is going to be the case for this specific example. So depending on the number of k, first the K-NN algorithm compares that single new sample to every sample in the database, or at least in the training data. So when it does that, then depending on the k, it chooses the first 3 samples, or if k is 5, it chooses the first 5 samples. So when it chooses the first 3, you can see that 2 of those 3 were funded. So if we choose k equals to 3, it's going to be a funded case. If k is 5, it's going to be a not funded case, because 3 out of 5 is actually not funded. So we generally decide that this application is going to be not funded as well. So K-NN is very sensitive to samples and also sometimes the k value. And what we could do is we try to choose the best k, and the way that we could do that is that we could, because it depends, if our model is not big enough, it's not a very big model, then what we could do is that we could train our model, like train and test, which is actually the score of our model. We could do that for different values of k. So here what I've done is that we created values from 1 to 20, and for each k in that range, we created a k nearest neighbor classifier with number of neighbors equals to that k, which is one of those 20. Then we train our model here, and we evaluate our model here and append that to a list. So this is a list of scores. And then we create a plot, plt.figure, x is k and y is accuracy. So this is the k, this is the accuracy. And we create a scatter plot. This is a scatter plot that I mentioned that it's a good plot for visualizing the relationship between 2 variables. And we just basically, for 1 to 20, on the x, we plot the scores. and these are the ticks, which are this part and this part. Actually, these are these values for the x. So we showed 5, 10, 15, 20. So what we have here is that we can see that as the number of k increases, the accuracy kind of goes higher. So if I want to plot something here, it seems that like that on average, like we have, as the number of k goes high, we've got a better accuracy. It seems like if I want to choose the best one, it could be maybe 14. But if you don't want to go that far, other cases around here might be 1, 2, 3, 4, 5, 6, 7, 8, or 9 could be a good case as well. So that was the KNN algorithm and how it works, and how we could go beyond and find the best parameters for it. The next step, which is also a very important step, communicating the results to the stakeholders. So in order to communicate the results to the stakeholders and also project sponsors and other executives, you want to first consider the fact that we have two different kind of audience. One audience is are the people who are maybe fairly non-technical, like they know, understand the concepts, but they're not that technical. And we have another presentation for the analysts. So if you are going to present your finding and results to project sponsors, executives, those types of stakeholders that care about the business value of your model rather than the technical details, then you want to make sure that you include the findings, recommendations, and the next step. So the main high-level findings and recommendations, next step, something that some insights that I call actionable. So actionable insights. So actionable insights is the most important thing that you could provide to someone. Maybe they decide to not to choose this project. Maybe they decide to go forward with it. Whatever it is, it should be actionable. If you just say, well, it seems like to be, you had a good year last year. Okay, they already know that. What is going to be the next year? What is your prediction? And what are the next steps to actually make sure that we have an accurate predictions? Do they need to, for example, create a new data set, hire a new person, start a new project, and then build this and create a dashboard and then deliver this dashboard to all their underwriters? Is that what they need to do? How long is that going to take? Sometimes you need the help of the business analyst to make sure that they are these steps are feasible or not. But when you want to create a presentation for the analyst, then you could include more technical stuff there, like your code, your metrics, your ROC curves, the distribution of the data, the different steps that you made to clean the data. You could include that presentation for analysts as well. Another key activities and the results that your project should have is the code. So what is the code of your project? You need to provide that to the team. And technical specifications for implementing the code in a dev and production environment. So you need to tell them, like you say, oh, this is a code that I wrote and I use a few libraries. I don't remember what they were. Okay, just leave me alone. I just want to find another job, or my internship is over. No. You should provide them with technical specifications, a step-by-step documentation that tells them what to install, uh, wants to add, what to add, where the data is coming from, the code that you provided, how it applies, and then where is it saved. Um, all the versioning of all the applications that you, all the, I don't know, libraries that you've used, and so on. And you have to make sure that you provide that specification to them as part of the documentation. And there are two environments. One is dev and one is a production environment. So development environment is an environment that usually it has a different data set. Like there's a, okay, let me explain this to you. So in a company, is it in a professional company, in any IT business, there are usually a few environments. So that environment means a set of data sets that might be in that environment. There are websites that are maybe in that environment, and one is called the prod or production, is the data set that the end users are actually connected to and they're using it. It could be quite expensive. It should be very fast, high quality, high reliability. It should always be available online. You see, if like a bank, like, I don't know, TD Bank, RBC Bank, any of the banks, if their services are down even for 5 minutes, like potentially millions of customers are going to be affected by that. So that is a production environment. So the production environment should be very big. It should be distributed, and all that. So if you want to create a change, like you provide a new solution, then your new solution will not be added to the production environment at once. It is going to be added to like a small environment called the dev environment. And so you apply it there. Dev is usually a small duplicate, a duplicate of the production environment that you could play in it. And there's also a staging area. There are different, there's a Q&A. So it differs between in different companies. Sorry, the QA, quality assurance. So sometimes there's this staging that is happening. So if you're working in a company and there are some specific implementations of how to deploy your code, and it's different for development and production. For example, the IP addresses could be different, the databases could be different, a lot of things could be different. So you have to make sure that you provide both of those information, so that if you just provide the production environment, no dev environment, then it's gonna negatively affect the whole product, and they could never be able to run your code because they can't risk their production environment to go down. So when you provide that kind of information and the code and technical documentation, that's mostly in the operationalized phase, when everything is basically finalized, the users accepted your results. And in this case, you may need to onboard new team members. So there could be new team members that needs to be added to make sure that this project is going on continuously. You may need a site administrator. You may need a data engineer. You may need some data scientist other than yourself to continue working on this. You may need trainers, people to train the underwriters to tell them about the new process. There are change management processes. So there are change management processes that should happen, and business analysts, business process engineers, like data project managers, they're going to be all involved to make sure that people who are actually trying to use this new product are aware of the changes and how it's going to affect their business processes. So if their original business process was that there was a person, like a client, and then applied online, and then the underwriter would see that. So that is the old process. So the new process could be something like, so person 1, person 2, person 3, and to P5, they all apply online, and then the it goes to your model, data science model, and the top one, or top, I would say again 20%. Top 20% will be given to the underwriter. So these underwriters, they should be aware of the situation. If they're not aware of it, then if that top 1% is not a good one, they should be able to access the other clients as well. They may want to get the top, like they just want to get all of them listed and sorted as 1, 2, 3, 4, 5 instead of just getting the top one, because they may say, oh, this guy, I know this guy, like he didn't talk with me very well, I'm not going to find him anyways, so let's go to the next one. For any reason, they may want to go and see the next ones. So make sure that everyone is aware, and as part of this operationalization, you have enough people to onboard. And then when you deploy the model, you need to make sure that you monitor its performance and monitor the people's performance as well. It may not necessarily be your job, but my experience, and if you had any experience with any tech companies, is that usually DevOps, like development and operations, and also like communicating with the customers, it's not that as easy as it sounds, and you will have a lot of business users that you're going to deal with and talk with to make sure they're satisfied with the product. It's not just that the model works very well. Actual people are going to use your model, so you have to make sure that those people are happy about it and they're going to use it very well. So even after you finish and finalize that final step, operationalization, then it does not mean that the work is finished. Maybe one cycle is finished, but you need to continuously monitor your product. And I mentioned that again before. You need to get new data. You need to monitor that your model is going to be working properly for the new data. So your model needs to be monitored properly, and sometimes new attributes can be considered. With the COVID-19, a lot of things, like a lot of processes have been changed. So a lot of new attributes are added to all the systems. So this is kind of a normal process that things could change. And also you may want to, I don't know, like add some different scenarios, like you want to create a delivery mechanism that could provide self-service reporting to the clients. So instead of like a person or a client, imagine that a client goes to the website, enters all their information, clicks submit. So instead of this going to the underwriter, and then the underwriters should get back to the client, you could literally remove these and give an automatic feedback to the user that, well, it's probably not going to be funded. Like call this number, or it is going to be funded, call this number, so that they can tell you. So you may want to provide some information as your model is becoming more accurate and accurate. Then you may want to provide a self-service reporting to your clients as well that says, well, it seems like with the information that you provided, you need to save some more money or find a new job or just go to live in the suburbs or like choose another mortgage. Like choose another house, you know? So some of that information could be provided to people. So to summarize, you have learned how to reframe a business problem as an analytics challenge, and then how you could do data preparation, data modeling, how you could try to tell a story. You see, this is a story that was told from the start to the end, and following that kind of step-by-step scenario, and kind of 1, 2, 3, 4, 5, 6 steps that you had from discovery to data preparation, model planning, model building, communication, and operationalization. So those are all the steps that we have covered so far, and I provided a step-by-step scenario, and you know that what you know about the key deliveries of your analytical project. So based on this information, you need to make sure that when you write your proposal, you need to find a business problem that is related to data science, or like any other problem that fits one of those categories. So you need to find a problem. You need to write your problem as a challenge, like you need to find that research question. What is the business question? What is the business problem you're trying to solve? And what is the output that you're going to probably have? What type of algorithm or problem do you have? Is it a classification problem? Is it a regression problem? Is it something that can be used using deep learning? So usually a clustering algorithm, if it's not dealing with something more complicated, is not just enough. You need to do some prediction. You should either work on creating a data set, or the model itself. Like the most important, challenging, interesting part of data science could be the data science models that are being evolved every day. However, that part usually falls into machine learning. But the data science process itself is something that starts from the data and ends with the presentation. So, so for your proposal presentation, you may want to have a report that covers all these 6 steps, your idea that where the data is coming from, and what you have in mind for all different steps. Because your final, I'm sure that you don't have a lot of information regarding the last 3 or 4 steps, like how you're going to plan, build your model, what are your results. But I would strongly recommend you to try building a prototype right now before you propose, so that you know exactly what's going to happen, and you have an idea of what is going to happen in the next months. So for you to test some of your knowledge, there's this site Stepic that you could go to. You could search for Introduction to Data Science Fundamentals 842 at University of Regina. And I already let you know that you could cover some of the questions there, try to answer them, try to implement the code. There is no limit on how many times you try as far as you can until you can solve it. And make sure that you complete them because it's going to help you a lot in understanding and making sure you understand all the topics. So if you have any questions, let me know. And yeah, you can connect with me again using the usual tools from Microsoft Teams to UR courses, and those are the preferred methods. And yeah, if you have any questions, let me know. So you can read this yourself. That an ideal data scientist is someone who has both the engineering skills to acquire and manage large data sets, and also has the statistician's skills to extract value from the large data sets, and also the skills to present that data to a large audience. So that's why we're going to focus on all of these in this course. The engineering skills, like statistics, and also presentation skills. Okay. Yeah. Thank you very much. And these are some of the sources that I used for these slides.